Thanks very much for the nice introduction, and welcome everyone to my talk, which is on neural implicit representations that we have been working on for the last 2.5 years or so. And it contains some of the introductory materials, some of the what I think is the most influential work that we did in this area, as well as a little outlook on where people are using these models today. And I really appreciate if questions are also asked during the talk. So if you have a question, just speak up, please. So this talk is structured into 5 parts. In the beginning, I will motivate why we are interested in this type of implicit, or some people also call it coordinate-based neural representations, and how we can train them from 3D supervision. And then in the second part, I will talk about how we can train these 3D representations from just images alone. And then I will move on to neural radiance fields, and in particular some works that we have done in this area that try to build generative models for neural radiance fields, and in the end some applications and whatever people are doing with these representations. So let's get started with implicit neural representations. If we want to reconstruct 3D from images, the traditional 3D reconstruction pipeline looks something like this. The input is a set of images. We first estimate the camera poses, that is the intrinsics and extrinsics, for example, using structure for motion. And then we can find dense correspondences using binocular or multi-view stereo, which give us some 3D representation, partial 3D representation of the scene that we can then, for example, fuse together into a more coherent 3D representation of the scene. However, recently there have been a lot of 3D datasets becoming available, and so the question is, can we use this 3D information for learning better models to reconstruct 3D, maybe even from a single image? So in the simplest form, that would be just maybe a neural network like this that takes as input a pixel matrix, just a single 2D image. And as we humans can also infer the 3D structure, tries to infer the complete 3D structure from just this 2D pixel matrix. Now, the input representation that we give to that network is pretty standard. It's a 2D pixel matrix, and we can use standard 2D convolutional networks to process it. But the question is, of course, what is a good output representation for a neural network to predict a 3D structure? And that's what we're going to ask here. And so there's a couple of output representations that people have considered in the past. Foremost, the voxel-based representation, which is a very natural 3D extension of the standard 2D pixel matrix. And so we can process it using standard 3D convolutional networks. And then there have also been, people have also considered point representations, for example, in this work, point set generation networks, or mesh-based representations like in AtlasNet. However, all of these representations are limited in that they discretize 3D space. So for example, voxel-based representations have to define a canonical coordinate system, and then they are heavily limited in terms of their memory constraints, the memory constraints of graphics cards where we want to process this information, because this memory just grows cubically with the resolution of the 3D space. Point-based representations also discretize 3D space, and existing point-based methods typically can only process or output points in the order of a few thousand. And also point set representations don't represent the surface directly, but just a loose point set. So there's no connection, there's no surface representation without any additional processing, like Poisson surface reconstruction, for example. And a mesh-based representation also discretizes 3D space, now this time in terms of vertices and faces. So here on the top we can see a 2D illustration. I forgot to mention this. And 3D illustration, just to simplify, I also drew the 2D, like a 2D cut through this representation. And so for meshes, it's particularly hard, from my experience, to predict meshes with neural networks, because all of these things like self-occlusions and changes in topology and representing a mesh as an output such that the mesh is homogeneous and uniformly represented in terms of its vertices. So this is very hard to do with a neural network. And so the question is, can we do differently? And that's what we pursued with our work on occupancy networks that is now already 2.5 years old, CVPR 2019, or even 3 years old almost, where the key idea is to not represent 3D shapes explicitly, but instead to consider the surface implicitly as the decision boundary of a nonlinear classifier. Now, implicit surfaces have been considered before, of course, and they have been considered primarily in the sense that we're generating a voxel grid, and then for each of these voxels, we are storing a sign distance value or an occupancy value. But what we are trying to do here is to use a neural network, a multi-layer perceptron, for example, itself as the representation of the 3D structure. So the decision boundary of a neural network that takes in a 3D point and some condition, for example, a 2D image, and outputs the occupancy probability, the decision boundary of this, like 0.5, defines the surface. And the parameters of this neural network, theta, called here, the parameters of this neural network are the representation of the shape. Okay, and so we can condition this on an additional input by simply conditioning this MLP here, this neural network, on this additional input, like a global encoding of an image or a 3D point cloud or a voxel grid. And here on the right, we can see an example of this in the 2D case and in the 3D case, where we have a decision boundary that separates the red from the blue points. And similarly here, we have the decision boundary separating the red points which are inside that bench from the blue points that are outside of this bench. And we want to basically train the parameters of this neural network such that the separation is as good as possible. So in this case, the function f theta models an occupancy field, but it's also possible to model different types of fields, and various different types of fields have been pursued, and we'll see some of them in this presentation. So one example, actually a work that came out at the same time as ours by Park et al., uses sign distant fields as an output representation that also have some nice properties. For example, easier to actually find the surface intersection, because at any point you know how far you are from that surface, right? So it's not just binary. So a very simple idea. Now, what does the network architecture look like that we used in this first work? It's also very simple. It's basically just a residual network. So here in yellow, we see one block of this residual network, and we use 5 blocks where we input the points here at the bottom, and we input multiple points at the same time, because it would be wasteful just to process single points individually. And the network can simply take multiple points at the same time, a whole batch of points. So that's why we have t points times 3, which is the x, y, z coordinate. And the network, after these 5 residual layers, outputs for each of these t points the occupancy probability. And in addition, this network is conditioned on a input encoding. For example, these are 3 different options. For example, we use a 3D convnet to encode a coarse voxel representation into a global latent code, like a 128-dimensional vector. Or we use a pointnet to encode a point cloud, or we use a standard 2D convnet to encode an image into such a global latent code. And that code is injected in at multiple places of this residual network, in this case using conditional batch norm, but you can use other mechanisms. You can also just concatenate the vectors. So this is how the condition is introduced into this model. And now the question is, how can we train this model? How can we train these parameters of this model, of this residual network, given that we are provided with input-output pairs? That means we have access to the input images, right? And we have also access to the ground truth. Like for each point that we give as input here, we have access to the ground truth occupancy state. So we have these data label pairs, and we train the parameters of both this residual network as well as the encoder. And so how do we train this? Well, this is a simple, in the case of occupancy, a simple classification task. So we can use standard binary cross entropy. So we sum over all the points in the mini batch k, in this case is 2048. And then the binary cross entropy loss compares the prediction that the model makes for that particular 3D point and that particular condition. This is the 128-dimensional vector here, to the ground truth occupancy of that 3D point, which we assume to be known in this case, as it's fully supervised in 3D. Right, so we take ShapeNet 3D models and we sample points, and we make these models watertight, and then we know which point is inside and which point is outside. We can also use this model in a unsupervised fashion, train this model in an unsupervised fashion, using a standard, for example, VAE objective, as we do here. We call this a variational occupancy encoder. But it's just a standard VAE where we have the reconstruction term, and in addition, we have this Kullback-Leibler divergence between the prediction of the encoder and a standard Gaussian distribution, just like in a standard VAE. Now, as this is an implicit model, we don't get a mesh out of this model directly, so we have to extract that mesh after training the model. And how do we do this? Well, we can query this neural network at any point in 3D space. And so we do this in a hierarchical multi-resolution fashion by building incrementally an octree that queries incrementally this occupancy network. So in this example here, we have this shape. So we query these points on the grid. The red point is inside and the other points are outside. And then we can mark the voxels that are adjacent to points that are inside and outside. And then we can subdivide those further. And then we can query the network again, and we can iterate this n times until we have reached the desired target resolution. And we can extract the triangular mesh using margin cubes. So let's look at some results. So here we have the input image on the left, and we have the reconstruction on the right, and we can see some baselines, a voxel-based baseline, a point-based baseline, a mesh-based method, and finally our results. And you can see that the results are quite smooth, and naturally, by design, this model handles arbitrary topology because we are using an implicit representation. So the model is quite smooth by design because there's some intrinsic smoothness properties of these neural networks that we exploit here that induce a bias towards smoothness. And at the same time, we handle arbitrary topology. Here's another example where the input is a point cloud that's encoded using a point cloud encoder. And on the right, you can see our result for this particular input point cloud. We can do the same for a voxel-based input, where we effectively super resolve. We learn to super resolve this voxel data that we have. And then now we can look at also some results of this unsupervised trained autoencoder. And what we see here is some latent space traversals where you can see how it interpolates between different shapes. So you can see it's not perfect, but it's also, of course, very hard to interpolate between very different shapes. Okay, so we can go one step further. One thing that we didn't consider so far is appearance. So how can we handle appearance? Well, we can handle it exactly the same way. For example, in this work, which we call learning implicit surface light fields, the input to this neural network is not just the 3D point location, but also the view direction and the light location. And if we do this, then we can model surface light fields where the view and the light position can change, and naturally model things like shadows and reflections, so view-dependent illumination effects. And so here are some results of this. Again, there's an additional condition on the input which in this case is an image. And here's a simple naive baseline. It's a 2D image-to-image translation baseline, which we wouldn't expect to perform very well because it lacks 3D reasoning capability, but it does something. And here is our results, where you can see that is, of course, is 3D consistent by design, but it's also able to model shadows and reflections. Now, this is for an example. This was for an example with a ground truth 3D shape, but of course we can combine this with the previous model and infer both the shape and also the appearance. One thing that we also looked at is how can we represent motion with this model. Unfortunately, we found that extending this idea of occupancy networks to 4D is hard due to the curse of dimensionality, and because shapes are very discontinuous, and representing something that's discontinuous with a neural network is hard. And also another problem with this is that there's just much fewer data sets that have shapes in motion compared to data sets with static 3D shapes. And so we have a data problem as well. So what we do here instead is, instead of representing things in 4D, is to represent the shape at time 0 or an arbitrary time using a 3D occupancy network, and then represent the motion illustrated here on top by a temporally and spatially continuous vector field. Now, this vector field is, of course, a 4D field, right? You have to define a vector, a velocity vector for each point in space and time. But the advantage of this is that this field can now be extremely smooth in order to represent the motion of a shape over time. And it doesn't have these nasty discontinuities that a shape has over time. And it's the relationship between the the velocity or the location of a point in time and the velocity is given by a simple ordinary differential equation, which is simply saying, well, the derivative of the location is the velocity. And because we know how to backprop through ODEs, we can directly integrate this into our into our architecture and train the parameters of the model by backpropagating through this ODE. So here are some results. Now, this is, of course, like a very difficult example where we have very noisy and sparse input points. So here's some baselines. You could see like how here on the left, the naive extension of the occupancy network to 4D space really suffers in representing detail, while this occupancy flow network can capture the details. And also, despite we don't need to provide correspondences to the model, we just provide basically reconstructions at each time step as supervision. The model implicitly automatically establishes correspondences, which you can see here by the consistency of the color when it moves, right? So you see that the same part has the same color when it moves over time. And so the model automatically learns to do this because this is the simplest explanation they can do for representing that space-time structure. Now, one limitation of these occupancy networks is, well, there's two limitations actually. So one limitation is that we are using a global latent code. So we have an input that's encoded into this 128-dimensional feature vector. And of course, it's very hard to represent complicated compositional scenes with that feature vector, with that single global feature vector. So there's no local information contained, and it leads to overly smooth geometry. And the other problem is that we use a fully connected architecture, which doesn't exploit, for example, things like translation equivariance that we would like to ideally exploit, because we know it's a useful property not only of 2D images, but also when when processing 3D scenes, like scenes of indoor scenes. Yes, and so these limitations lead to these models work very poorly when we move away from single objects to more complex scenes. And this is not really a complex scene that I'm showing you here. On the right is the ground truth. And on the left is the result of the standard vanilla occupancy network. But you can see how hard it is for the occupancy network to model this compositional structure with a global latent code. It's just extremely hard. So all the geometric detail is gone here, basically. So what we propose here in a work called convolutional occupancy networks is to, instead of doing that, to combine the idea of implicit null representations with 3D convolutions. So what we do is we take the input, in this case a point cloud, and then we encode this into a coarse 3D grid from which we can query features at arbitrary 3D locations continuously using trilinear interpolation. And then we put these features and the location into a smaller fully connected network and output the occupancy probability. And now through this 3D grid structure, we can employ 3D convolutions that leverage equivariance, and at the same time we can make the capacity of this fully connected network smaller, which leads to these benefits. I do have a result for this as well. So here we can see what this gives us, the input, and here in the middle the result. And even if we just train on synthetic data and apply this on real scenes, on real scans, it works quite well. So here's an example where the input is from ScanNet and the output is the inference result, where it has been only trained on synthetic data. And this is a result when applying this model that's trained on synthetic data on larger scenes like Matterport 3D. So this allows us to go not just to capture more detail, but also to go to larger scenes. Yeah, cool. So let's move on to moving on from 3D supervision to 2D supervision. So far, everything has been completely 3D supervised, right? So we needed 3D ground truth, and we know that in many cases it's not available. And so ideally, we'd like to train these models just with 2D supervision. And there is differentiable renderer, for example, for mesh-based representations or voxel or point-based representations. So we were wondering, can we also have a differentiable volumetric rendering approach for this type of implicit models here? The architecture that we consider is quite similar to the architectures that I've shown you before. We have a condition, like an image that's encoded with an image encoder into in this case, a global latent code again. And then we have a set of points that are passed at the same time through these residual blocks. But now in this case, we predict at the same time both the occupancy and the texture, right? If we want to render an image, we need to have the texture. So we need to predict both shape and color at the same time. So for each of these 3D points, we predict occupancy, this is a one-dimensional quantity, and texture, RGB. Now, in order to train this model, we need to define the forward pass and the backward pass. And the forward pass is just a standard rendering, as we would call it in computer graphics. So how can we render such an implicit representation into an image? Well, that's rather straightforward. So what we do here is so here what we can see is the image plane and the camera center and one particular ray that goes through the camera center and that pixel U on that image plane, and that goes into the direction W here in green, and that intersects the 3D structure at this particular point here, where the structure in this case here is represented by the level sets of our occupancy field, where the thick line here represents the actual surface. This is basically the 0.5 level set, if you will. So if tau is 0.5 here, and then we have values of that occupancy field that are larger than this and values that are smaller than this, so values that are behind and front of the surface. So this is how this occupancy field is represented here in this simple illustration. So what we do now is we go through all the pixels in the image and find the surface point P hat along the ray W by first marching along the ray and figuring out at which point, so we march at relatively coarse steps and figure out at which point the function or the field changes from being smaller than the threshold to bigger than the threshold. So we know the intersection must be somewhere in between here. And then we can simply find the root of this function using, for example, the second method. So numerical method that can find the root of a function. And then once we have found the root of that function, we can evaluate the texture field. This is the second head of the network that was shown before. And this gives us the color at this particular 3D location. And then we can simply insert that color at that pixel location. And if we do this for all the pixels, we get the image. So far, so good. Now the question is, of course, how can we define the backward pass? How can we differentiate through this backwards? So what we want to do is we have an image observation now, and we want to minimize the prediction error. So we want to minimize the difference between the prediction I had, the predicted image, and the observation, the actual image I. So we can use a standard loss function that, for example, compares the per pixel L1 or L2 differences. So we sum over all the pixels U here and compare some norm here. And then what we of course want to do now is we want to compute the gradient of this loss function with respect to the parameters of the network, the parameters of the texture and the occupancy network. So let's do that. So the first thing you need to do is, well, we can use the chain rule to compute the derivative of L with respect to theta. So this is the sum over all pixels of L with respect to I hat. That depends on the parameters theta. This is the prediction, times I hat with respect to theta. So far, so easy. Now we want to further decompose this term here on the right. And I hat depends on the parameters theta through both the texture field that is evaluating the color, but also through this location p hat, because that location p hat, the surface intersection, changes if I change the parameters of the occupancy network, right? Because then the structure changes. So p hat also depends on the parameters theta. It's not explicitly mentioned here in this formula, but it depends on it, which means we need to use the total derivative. So that's why we have a plus here. Now the first two terms here in black, they are easy to compute. This is just a neural network, so we can use standard backprop to get these gradients here. But how can we get this term here on the right, which is the derivative of the surface intersection point with respect to the parameters theta? And what we can do here now is we can differentiate, we can use the implicit differentiation of the level set constraint. This is this constraint that the surface this ray must intersect the surface at the value tau, say 0.5. And if we do that, if we do implicit differentiation of this level set constraint and rearrange the terms, we get such a closed form expression here on the bottom. And so we can see now the terms that depend on the parameters theta, right? These are the texture and the occupancy network that have a shared backbone, as we've seen before. And so we can update now those. And this is illustrated here, so you can see how the optimization changes both the color. I try to visualize this here. Changes the color and also the geometry, right? So we have we have found an analytic solution, and there is no need for storing intermediate results like in, for example, voxel-based approaches where you ray march through a voxel representation and you need to backpropagate to all the voxels along the ray. We don't have to do this here because the representation is a multi-layer perceptron. And through the implicit smoothness properties of this multi-layer perceptron, automatically this information is propagated in 3D space. That's how you can think about it. So this is really nice and also quite fast. So let's look at what this does. So the first thing we did is, again, this per image conditional learning an image conditional network, but now without 3D supervision. And so here are some results. You can see how this works. This is our result with just 2D supervision. You can see it's not perfect. If you use 2.5D supervision, which of course is also possible through this differentiable rendering paradigm that I've just shown you, you can also backpropagate gradients in terms of depth map, right, values. Then you get better results. But in principle, it's possible to train only from images. So here's another example with a car. Now this, of course, this is not the training process. This is basically the inference. Then, like, we're giving a new image to the network, and now at inference time, this network predicts this, right? But it has been trained on a large collection of different images of different cars using just this image loss. And we can also use this model now to like if we don't condition on the input image, we can use it for reconstruction, 3D reconstruction of a single scene by optimizing this model for that single scene, and we get 3D reconstructions. And we've demonstrated this on the DTU dataset, and we get nice watertight meshes. Now, of course, these results are a little bit superseded by more recent methods that, for example, also model view-dependent effects that we haven't modeled in this work here. But they are considered in neural radiance fields, and that brings me to the next chapter. So probably many of you have heard of NeRF, so I don't need to talk too much about it. The idea is very similar to the ideas that I presented before, actually builds on those, but the representation is slightly different. And the task is, the main task is also slightly different. So the focus is to, given a set of images of a scene, render an image from a novel viewpoint. So the main focus is on getting a good novel view synthesis results. However, of course, in order to get good novel view synthesis, you also need to estimate the underlying geometry. So what they do is they basically also use a ReLU MLP that also maps the 3D location and the view direction, like in our light field model, but in this case to RGB and the density. And in contrast to the surface rendering that I've showed before, they're using volume rendering. So volume rendering works very similar to traditional ray tracing in graphics. Instead of finding the surface point exactly, you shoot a ray, and then you should race through the scene and then sample points along that ray, and you query the neural network for the RGB color and the density, and then you simply do alpha composition in order to get the pixel color. And they also demonstrated that these Fourier features, if you pass the input 3D location through such a Fourier feature mapping, expand the dimensionality of that, you can get much improved visual fidelity due to this, to combating this implicit smoothness bias of these MLP representations. So that's also advantageous. One big benefit of this type of representation is that you don't require any masks like the previous approach that I showed you, DVR, has required mask for training because it wasn't able to handle a background. But here you don't require masks. So this model is much more graceful. It can basically synthesize fuzzy stuff and alter that over time into the right structure, and so it's much more general in terms of the scenes that it applies to. And so there have been really nice results. I guess you have seen those already, which have really impressed the community and fostered a great interest into a great renewed interest into this application of novel view synthesis. Now, one big problem of these NeRF models is that they have to sample all the rays, and because every time you need to evaluate a big MLP, it's very slow. And so in this work here that we presented at ICCV last year, we've demonstrated that you can do this actually much, much faster by, instead of representing the entire scene using a single big MLP, to represent the scene using many really tiny MLPs. Many low capacity MLPs, you get even a little bit better quality, and you can do things like empty space skipping and early ray termination to overall, with all of these three components added, gain about more than like 3 orders of magnitude speed up. So you can render this now in real time. I want to show you quickly a comparison of like what this looks like. So here, this is a comparison to the NeRF baseline, and this is what NeRF can render at real time. It's a 19 by 19 pixel image, and on the right is what KiloNeRF can render at real time on a standard, not even super sophisticated, standard 1080 Ti graphics card. So there's ways to make a rendering, volumetric rendering fast. So there's the potential for these representations to, at some point, replace or complement existing mesh-based representations in computer graphics. Now, this was just a little bit of a prelude to generative radiance fields that we have investigated. that are trying to now use this radiance field representation in a GAN-like setting, where given a unstructured and unposed 2D image collection, we want to build a generative model of the underlying 3D structures, which is of course a very hard problem. The problem is that we can't discriminate in 3D because we don't have 3D ground truth, we just have images. And volumetric rendering is slow, so we use a patch-based discriminator like in a patch GAN. But the overall principle is illustrated here. The input to this radiance field representation G, that is again a mapping from a view direction and 3D point location to color and density that can then be volumetrically rendered into such an image, is like a sample from like a 3D point location, but then also a sample from latent space that determines the appearance and the shape of the object. So here's a little bit more detailed view of this model. We have this radiance field G that maps a 3D point X and a view direction D to color and density. So it maps the view direction D and the 3D point to color and density. And by sampling n points along an array, we can render a pixel's color. It is called a conditional radiance field because in addition, we condition on a latent shape code and a latent appearance code. And we structure this architecture of the conditional radiance fields in a way that these two latent variables are automatically disentangled through the inductive bias of the architecture of G. And then the generator repeats this process for R rays that are sparsely sampled on a 2D grid. This is this patch-based GAN that I was mentioning before. And the camera intrinsics and extrinsics and these grid parameters are drawn randomly from some prior distributions. And so we can, now given this mechanism, we can predict or render a patch for this particular camera pose and this particular patch sampling pattern and this particular latent code of shape and appearance. We can now render this patch, and we can similarly to this generator extract real patches using similarly sampled sampling patterns, and then we can compare those two using a patch discriminator. And this is a very simple patch discriminator now. It's just a few convolutional layers because these patches, I mean, in this illustration, it's 5 by 5, but in practice, we use 32 by 32, but it's really just a neural network, a convnet that operates on 32 by 32 patches at all times, independent of the actual image resolution or the capacity of the neural network, because we always render these 32 by 32 patches. So it's a simple 4-layer convnet in this case of graph. And now this allows us to, we were quite surprised ourselves to get quite reasonable results for the shape and the geometry of the 3D structures that we want to infer. Remember again, this is trained only on, oh, let me move back. This is trained only on a collection, an unstructured collection of unposed images. So we don't have the pose, we don't have the intrinsics and extrinsics of the cameras. We just have images. And the model comes up with the 3D structure. And we can see this, for example, by rendering the depth maps, right? There was no geometry information, no depth information provided as input to the model. But in order to explain these images, the model has come up with a depth representation that's quite realistic, where you can even see like things like details like this mirror, for example. And you can see view-dependent effects emerging as they were present in the original image. And you can then change the geometry and the shape and the viewpoint of these generated samples. And we can also do this for faces and birds and cats. Yeah, and so we have done an extension of this that we have presented at CVPR 2021 called Giraffe, Compositional Generative Neural Feature Fields, where we, in addition to disentangling shape and appearance and training from unstructured image collections, here we also train from unstructured image collections, but in addition to this, we also disentangle different objects in the scene. So you can see we have a radiance field or a feature field here in this case, actually, because we render feature images and then they decode this into higher resolution images for efficiency reasons. But we have, the important point here is that we have these different components where we have different fields that we stitch together using a weighted, a density weighted combination of these different fields here to yield the overall scene, where we have the background element here in the bottom and then different objects here at the top. So this disentangling happens automatically through this model while it's trained on unstructured and unposed image collections without this information. This is, for example, semantic segment. So here, what we can do now with this model is we can generate new examples of the scene with new objects placed at specific locations. And we can see that a 2D based GAN, if you use just a standard 2D GAN, is not able to disentangle these factors. So if we change a particular latent dimension, we can see that an object maybe moves, but it doesn't move linearly, and another object changes color, so it's not disentangled. And we cannot say, well, we want to insert an object at this particular location. But now in our case, we can do that because these objects have been disentangled, and we can move them as we like, and we can change their shape and the color because they have been disentangled. So for example, we can rotate an object around another object, but this would of course not be possible with a standard 2D GAN. We can change only the background. We can add more objects at test time. So this was a model trained on 2 object scenes, and now we generate scenes with more objects. So here are some examples on real images. This is for cars. You can see that this data set actually has a little bias towards cars that are frontal or side facing, and that's also incorporated into this trained model. We can then change the depth of the object. Or we can move the background, in this case for churches. Or we can change the background appearance. We can also generalize out of distribution. So we can go beyond the distribution that was present in the training set. So we can move further. Or we can scale further. Okay. Great. So now I'm coming to briefly to the final part, which is our outlook on applications that this type of models enable. And we have seen really a huge, I would say almost explosion of applications in this area. I just want to show you some of them. So what people have looked at, for example, here in Coin, is at compression. And they found that these representations actually also have nice compression capabilities. For example, this nerve-based model can represent a 3D scene in just a few megabytes. And similarly, you can train an MLP or maybe a bit more advanced architecture to represent an image. And then this image is represented by the weights of that neural network. And so this leads to compression. You can also apply this idea to stereo networks, to stereo matching. This is what we have done in a paper at last CVPR, where we have a standard stereo backbone, a state-of-the-art backbone, and then from the backbone, we can now query at subpixel locations features, and these features are input to an MLP that predicts, now in this case, a probabilistic estimate of disparity, and so we can get very precise stereo disparity maps at arbitrary resolution, at more than 4K resolution, that wouldn't be possible otherwise with discrete processing. And a similar idea has been proposed here also for in the case of instance segmentation, where you can see the mask RCNN result here on the left that uses a grid in order to represent the mask of the object, which is 2 cores in order to represent the detail shape of this tennis player. While if you combine this with this idea of implicit modeling, you can represent the shape much more precisely. You can also use these implicit models for interactive scene labeling. So in this case here, a model has been trained for predicting both geometry and semantics jointly. And because you train this implicit scene representation jointly, it comprises aspects of both in one single model, which means that if you just click a few points on the geometry, you can label the entire 3D scene pretty precisely because the model knows how to separate the different objects from each other. This is another application of NeRF, where NeRF has been used. It has been trained on several scenes. And the downstream task here is localization. And so if you train a NeRF model on those scenes, then you can, of course, generate novel views. So you can train your post regressor, your downstream post regressor, much better because you have a larger data set. So it's basically used for data augmentation. And there's a couple of other papers in that area that are similar. It has also been used to model and incorporate reflectance information. So here's an example from SciB, where they have used these type of models to not only model the surface light field, but actually the actual rendering equation. And in this case, implicit models have been used for space-time super resolution of turbulent flows with applications to physics. We have used these implicit models also for human body modeling. They can be used both for modeling skinning weights as well as for modeling the human body geometry with and without clothing, yielding results that go beyond the state-of-the-art, in particular when generalizing to out-of-distribution poses that are not part of the training set. So you can see here, for example, a very difficult pose where other models have problems. And this is a work where it has been demonstrated that you can also incorporate physics into these models. It's called differentiable rigid body dynamics with implicit shapes. And so they learn a differentiable rigid body dynamics model that incorporates things like mass and friction jointly with the geometry. So here's a recent work from Simeonov et al., neural descriptive fields, where they use these models for future generalization of manipulation tasks by predicting spatial descriptors for robotics applications. And then this is a work from our group in the area of self-driving, where we are representing the internal state of a self-driving agent using such a continuous representation that's trained for semantic segmentation and waypoint prediction jointly, and leads to self-driving as demonstrated here in this video. So this is a model that has been trained end-to-end for the self-driving task on Kala, predicting next waypoints and semantics, and uses that for driving. Okay, it's not driving here because a red light. Okay, so let me summarize. We've seen that neural networks can be used as continuous representations of shape and various other things, and there's various approaches that have presented this. Use this for mapping from some low-dimensional coordinates to some other low-dimensional quantities here, all slightly differently. So we've seen that these coordinate-based networks can be effective output representations for shape, appearance, material, and motion in this talk. They don't require any discretization, and they can model arbitrary topology. They can be learned from images via differentiable rendering, and there's many applications, for example, in 3D reconstruction, motion estimation, view synthesis, robotics, and so on. However, the geometry must be extracted in a post-processing step, which in the case of occupancy network takes around 1 second, and extension to 4D is not straightforward, as we've seen. Also, we've seen that this fully connected architecture has its downsides, and global conditioning leads to over smooth results. But there are some promising directions, for example, using local features like in conf or conf-onet, or better input encoding like in NeRF. Thanks a lot for your attention, and I'm very happy to discuss your questions with you. And by the way, there's also this link here, which is our blog. So if you're interested in our work, I invite you to have a look at our blog as well.
Great, amazing. Thank you for the amazing talk. Please, if you have a question, post it in the chat. I can read it then, or we can unmute you. Maybe to start things off, I can ask a question which I had. So in the beginning, you were using 2D or even 3D encoders to help you get the conditional representation. I was wondering whether the most recent state-of-the-art 2D encoders like vision transformers, etc., do they actually yield improvements for these relatively simple shapes, or is it all you need relatively low-level information?
Yeah, that's a good question. We haven't tried these more advanced architectures, which also were, I think, more recent than our early work that we did. I mean, there's certainly a limit, as I mentioned. Like, if you just predict a global shape code, then there's a limit through that. But I think, you know, if you use localized representations, there can certainly be benefits through using a better encoder, better backbone architecture always helps in a sense, right? So, for example, there's works like PyFu, where the where you run a convnet, and there could be something else, but you run some neural network on the image and you get per pixel features. And when you do, you then basically project the 3D point onto the image plane and you query the features from there. And so then through that, you retain local information. So it's similar to conv-ownit, which does it in 3D, but you can also do this through the projective mapping. And so I think in the case where you predict only a global code, you might get some benefits through a more advanced architecture, but there's certainly limits through the global code itself. But if you then move on towards more local conditioning, then I'm sure you can get better results. Yeah.
Right. Cool. Thanks. There's one question in the chat, I believe, which was asked when you were talking about the ray marching. Whether there can be multiple routes from the second method.
Yeah, so the second method is not guaranteed to give you you know, so it gives you one route.
Sorry, let me.
It can even diverge, so it's not guaranteed. So I think in our case, what we do, that's also the reason why we. Let me go back. Where was it? Yeah, it's also the reason why we basically first do ray marching until we are in the vicinity of this route already. And because this occupancy field in the vicinity of this route is already quite smooth, this method converges within just a few iterations and converges quite robustly. But it would probably not do something reasonable if you would start like with a very large interval without this route marching, without this ray marching. But what you can do, if you, instead of predicting occupancy, you predict SDF, then you can use a different algorithm. For example, you can use sphere tracing, and that gets you to the root much quicker than using this naive method that we used here, where we just sample in equal intervals, right? Because if you have the SDF, you know how far you are from the distance. You don't know how far you are from the distance along the ray, but you know how far you are from you don't know the distance along the ray, but you know how far you are from the surface. And so you can use this using sphere tracing to reach the intersection more quickly.
Yes, sorry, that was my question during your talk, and after a while, I really realized that it is a rather trivial question. My concern at that time was if you have a very thin structure, very thin 3D structure in the implicit implicit function, then it really depends, like maybe how much points to sample along the ray. But yeah,
that's true. So you need to sample more points along the ray than for thin structures, and that's also what we do. Yeah. So our focus. Yeah.
I have one more question. Like for the differentiable volumetric rent, you have the analytical gradient for the depth part. Can I understand that part as say basically you have the gradients of the gradients regarding to the 3D regarding to the 3D point in the implicit model is the surface normal, and you are controlling by it by W. It is about the direction of the ray. So it is just something like that.
I'm not sure if I understand precisely.
Okay. Yeah. It's like giving a tangent of the.
So what I can say is that like this great, like the way why we have this, the reason why we have this closed form solution is because we project this on the ray. Yes. And so it's basically but this is just what comes out of this equation. I don't know if it has an interpretation in terms of normal or anything. It's just like what falls out if you do like you basically, if you do implicit differentiation of this, you differentiate the left side with respect to theta and the right side with respect to theta. The right side with respect to theta is 0, and the left side you need to apply the total derivative. And if you do that and you rearrange, you get this equation here. And so because this is a projection onto W, it is a 1D quantity, and so you can invert it. If it wouldn't be a projection on W, then you might possibly not be able to invert it.
Yeah, I checked that derivation. It is quite neat, and
yeah. So we use that same trick also in our works. So for example, for SNARF, we also do it. We have a couple of other works where we use it in different contexts. So it's quite, for these implicit models, of course, it's using implicit differentiation is quite a good tool because it's needed often. But then not in all of the cases you can get a unique solution.
Yeah, thank you. I actually have some more questions, but Yuki, can I? Yeah, maybe I leave the time to others first.
Yeah, let's give Pascal the question, and then if afterwards there's no question, then maybe.
Thank you for your presentation. I have a question about implicit functions in general. So whenever I see them visualized, it's always with the Lego or something along the right, which makes sense. What if I have something like a flag or water or those kind of things? Does it still make sense, or is there something that's being looked at in the community? Can you comment on that?
A flag, you mean like
a
waving?
Flag, yeah, flag? A waving flag or moving water, or.
Well, if it's like this radiance field representation, the standard one is applied to static scenes, right? So it's nothing moving. It's assuming to be either static scene or a scene that's captured with multiple cameras at the same time. But there is now also dynamic versions. So there's dnerf, there's nerfies, and so on. So it's quite possible to capture some dynamics also in these models. Yes. So at least like short temporal dynamics within like 1 second. If you think about a waving flag or like wrinkles on the water, I think these are certainly within the scope of what these models can do. Yeah. Mm-hmm.
Cool. Thanks.
Yeah. So I didn't talk about these models in particular, but there is at least 5 or 10 extensions of NERF to dynamic scenes. Yeah.
Also, since we're already over time, just want to be mindful that we're not keeping you too long. So maybe
Okay.
you can ask your next question, and then if there's no other question, we can have it.
Yeah, thank you. And another thing maybe not mentioned in your talk, but something also in my experience, we see that Fourier features are widely used in neural radiance fields, not only for the optimized based setting, but also learning based setting. I think in your generative, in your graph, in your giraffe work, Fourier feature are also used. But in my experience in shape modeling, for example, in occupancy field, I tried with I tried to do that Fourier feature or the periodic activation in those learning-based settings, but it generates artifacts. It does not generalized well. And also,
Yeah.
I think also report by other papers. Do you have any remarks on that?
Yeah, I think, like, for example, Siren is a bit tricky to get working because you need to initialize it well, and it's in general a bit harder to tweak. The Fourier features, you need to be careful about the capacity, all right, and like the frequency bands and so on. So there's a couple of recent papers like Bacon that look into this and that try to regularize it, right, so that you don't get this artifact. So I recommend you maybe have a look at the recent Bacon paper. But also even in the initial papers that analyzes the Fourier frequencies, you have like you clearly see if you go too much towards the high frequency side, then you get noise, right? And if you go to the smooth side, then you get over smoothing. So there's clearly a trade-off. And so for geometry, often like appearance is more high frequent than geometry. That's why in practice, what we often do is for the geometry, we have less frequencies than for the appearance, right? So there's different Fourier encodings for the two.
Yeah, that's also what I was thinking about. The texture part, you have a lot of more high frequency signals. Yeah, thank you very much.
But there's also now ways to regularize better. So this is very recent.
So what's that paper called? Bacon?
Bacon, like the thing that you eat. Bacon,
Yeah,
which is in your hamburger.
Okay.
All right, cool. Then I want to thank you again for this great talk and the answers to the questions. And yeah, thanks everyone for attending. And yeah, you'll be hearing about the next QvA Deep Vision lecture soon. And have a great day wherever you are, everyone.
Thanks for having me. Good night, everyone.
Bye.
Thanks.